Welcome to the talk Raccoon, Automated Verification of Guarded Race Conditions in Web Applications. This was a collaboration between Simon Koch, Tim Sauer and Martin Jons from the Institute for Application Security and Giancarlo Pellegrino from the CISPA Helmholtz Center for Information Security. Probably everybody has been online shopping before, and in our example we are trying to purchase a pair of shoes. We put the shoes into the shopping cart and proceed to the checkout, which tells us that the value of the selected items is $200. However, we have a coupon that we can apply. Applying the coupon leads to a reduction of $100 of the shopping cart value. However, the value of the coupon was $100, and when we try to apply the coupon a second time, we're denied, as the coupon has been used up. How might the code for this process look like? This is a pseudocode example of the code that applies the coupon value on the shopping cart price. The function is called as soon as the user is asking the server to apply the coupon. And the first thing the function does is requesting the value of the coupon from the database. It then checks whether the coupon has still some value left, and then applies that value to the value of the shopping cart. After this, it updates the value of the coupon in the database accordingly. Finally, the function returns the new reduced price. What happens if the user now tries to apply the coupon a second time? The function is called again, and it first retrieves the value of the coupon from the database. It then checks whether the coupon has still any value left, and realizes that the coupon is now worthless, aborts, and returns the current shopping cart value to the user. What would happen if this process is performed concurrently by two users? Two users now try to apply the same coupon, and two such requests are performed. As we are using PHP, two independent workers are started simultaneously and call the function. Both executions now retrieve the current value of the coupon from the database, and both executions use the retrieved value to check if the coupon still has value. Both executions then proceed to apply the coupon value to the shopping cart and update the value of the coupon in the database accordingly. Finally, both executions return the new shopping cart value to the user. However, this behavior is quite unexpected, as previously we were only able to apply the coupon once. Now we were able to apply it twice. What happened? When we have a look at the function again, we can see that the first action performed is the reading of the current coupon value in the database. This is performed by each worker independently and at the same time. Thus, each worker continues its work with a value of $100 for the coupon. This leads both workers applying the coupon value to the shopping cart and updating the value in the database. Finally, both workers return the reduced shopping cart value to the user. This is a race condition due to the interaction of web application and database, or more precisely, a guarded race condition, as there is a guard involved that assumes that the previous reading from the database returns the correct and up-to-date value. This, however, is not the case, as both workers perform each action concurrently yet independently from each other, and the value of the coupon is updated after both workers have read the value from the database. Those guarded race conditions are the security vulnerability we are interested in. Database-based race conditions in web applications are not new. They were first described in 2008 by Pagliari and colleagues, who established the term interdependence between query pairs that could potentially exhibit the previously shown behavior. They developed an algorithm that is able to determine from a set of queries which query pairs are interdependent. For this algorithm, they depend on two functions, use and define. Both functions expect a query, and use returns the column read by the query, and define returns the column written by the query. If there is an intersection between the two returned set of two queries, those queries are considered to be interdependent. As an example, let's assume two queries Q1 and Q2. Q1 reads from the table coupon and Q2 writes to the table coupon. When applying use to Q1, we can see that Q1 reads the columns value and name, whereas when we apply define on Q2, we see that it reads the column value. When we calculate the intersection between the two returned sets, we can see that they intersect on the column value, and thus the two queries are interdependent. Thus, to summarize, the state of the art is that we have a model understanding of the issue, as well as an algorithm to use the model to find vulnerabilities. However, we do not have a way to automatically gather data, test for vulnerabilities automatically, and validates the test's results. We want to rectify this and present a method that is able to automatically gather data, apply the detection algorithm to find potential vulnerabilities, test those vulnerabilities, and validate whether or not a test had a positive result. We perform those tests on a use case basis, and we define a use case by a set of interactions with the browser, for example, buying something and applying a coupon to the price. To simulate a use case against a browser, we chose Selenium that takes a set of actions and automatically simulates those actions, imitating a human user in the browser. Such a set of actions is called a user trace. We incorporated those user traces into our testing pipeline. Our pipeline consists of first setting up the server, which has to be performed for each application that we want to test. The setup enables us to collect the data we require and later on interact with the server to enable testing. The next part of the testing pipeline has to be performed for each user trace and consists of data gathering, data analysis, and the testing and validation of the tests based on the previous steps. The data gathering consists of two parts. The first part is a two-time execution of the user trace. We collect the requests and execute SQL queries. Between each execution, we restore the web application to the initial state. The second part is the consecutive execution of the user trace without initial state restoration. Again, we collect the requests and executed SQL queries. We then use the data collected during the repeated execution and compare the URL execution step by execution step to isolate noisy elements of an URL. In this example, the parameter value of random is noisy as it changes between executions of the same step. We use this information then to sort the SQL queries that were collected during the consecutive execution into buckets representing the same request. We can do this now by simply comparing URLs, as we know what elements of a URL are static and which are noisy and thus need to be ignored. We use those buckets now to count writing queries and remove each such query that occurred as often as we performed consecutive requests. Remember, we are interested in guarded race conditions, and queries that were executed for each consecutive execution can be assumed to not be protected by a guard that limits the execution count. Consequently, they are not interesting for us. Finally, we use the remaining queries and apply the interdependence algorithm on a request-by-request basis, and collect the resulting interdependent query pairs. We then perform a test for each such query pair where we replay the user trace concurrently. However, we modify the database behavior to postpone executing the writing query for a time, thus opening up the window for a potential race condition to occur. We modify this behavior transparently for the application by using a proxy in between the application and the database that injects a wait. This ensures that we do not change the behavior of the web application in a way that would introduce a vulnerability in the first place. For the application, it looks like a long response time by the database. As during the data collection, we collect the requests and corresponding SQL queries. We then use the collected information during the consecutive and concurrent execution to check the bucket containing the writing query, whether or not the writing query was executed more often during the concurrent execution than during the consecutive execution. If so, we consider this to be a verified guarded race condition. The rationale is quite intuitive. If we go back to our initial example and look at the consecutive execution, we can see that the writing query was only executed once, as during the second application try, the coupon did not have any value left and the execution aborted. However, if we look at the concurrent execution, we can see that the writing query was executed twice. This is due to the guard that can only trigger if the reading query returns the proper value of the coupon, which it fails to do if multiple workers at the same time are reading and later on writing the value. We implemented our method as the tool Raccoon and applied it against 4 applications and 3 different use cases. We chose 3 web shops: OpenCart, AbundaCart, and Oxid, where we tested the login process and the usage of a coupon or voucher. We complemented the web shops with a forum application MyBB, where we tested the login again, as well as the flooding protection of creating a new thread or sending a personal message. As our generated test column shows, we were able to prune quite a few potential test cases initially detected by the interdependence algorithm by looking at the execution frequency of the writing query during the consecutive execution, thus reducing the overall required test times. We were able to find 6 guarded race conditions, 4 of which were novel and 2 of which, the OpenCart coupon and voucher vulnerability, were known before and represent a validity check for our implementation. The voucher and coupon vulnerabilities are critical, as they potentially allow an attacker to use a coupon beyond its actual value and thus inflict monetary damage. The login and flooding protection vulnerabilities are not as severe, but weaken the brute forcing protection of login forms and the flooding protection. Thus, they enable an attacker to try more passwords per time period or flood a forum with unwanted spam. To summarize, we presented the first automatic approach on testing and validating guarded race conditions in web applications, implemented the approach as the freely available tool Raccoon, tested 4 different web applications, and found 6 guarded race conditions, of which 4 were novel. Thank you for your attention. Have a safe and pleasant SAC.